Hi, I'm Ali. I'm a graduate student in computer science at Berkeley, and I'm going to talk about our work on inferring pathway models using temporal phosphoproteomic data. So, as we've seen in the talks before, there are many pathway maps that aim to explain the mechanistics of existing signaling pathways. Here's an example, the BioCarta pathway for the epidermal growth factor pathway. So what I would like to emphasize here is that these pathways are not suitable for studying specific cases, scenarios, conditions. And for instance, when we stimulated the EGFR receptor and performed a mass spectrometry analysis, we observed that 31% of the pathway showed some activity in response to the stimulus. Meanwhile, 98% of the activity that was given by the data was not covered by the pathway. So this motivates coming up with methods for specific, case-specific pathways that would explain more of this activity that is not covered by existing curated pathways. So the data that we use for this is first a temporal phosphorylation data given by the mass spectrometry analysis that will give us in one experiment a global view of how the system dynamically responds to the stimulus. So this does not cover all activity because not all activity is phosphorylation. So we have some false negatives, and there can be irrelevant spurious phosphorylation activity that we are not interested, which could be some false positives. This is why we also consider graph algorithms as our input to give us a subnetwork of a, let's say, large interactome as described before, and give us some high confidence connection that could be a sparse graph where not all proteins are phosphorylated in our data. So here, for instance, we have a gray node. That means this was not in the data, but was recovered from the interactome. And we can think of other inputs such as prior knowledge. In our work, we considered a curated database of kinase substrate interactions as prior knowledge of directions that we integrated into our approach. So we take these inputs, and our goal is to give these pathway models that are condition-specific, that are sign-directed models, so similar to what you would have in a manually curated pathway, and give some dynamic explanation as to how the system responded to the stimulus. So how do we achieve this? Our approach is to explore a large set of all possible models that we think agree with all the data that we have. So let's consider all network models, all ways of directing the undirected topology. And then we have, from the initial topology, we consider some constraints. We produce some constraints that say that all interactions that we infer in our pathway model must be in response to the stimulus. And so this restricts the space of models to some subset. And we add temporal constraints saying that the sequence of interactions that we infer in our models must agree with some temporal precedence information that we extract from the data. So now we'll be considering only the intersection of these spaces of models as our valid models. And similarly, we assert that all of the models that we infer must not violate the given prior directions that we take as known facts. So we'll be considering similarly here the intersection of these three constraint spaces as our solution. So in more detail, how do we produce these topological constraints? So we say that all interactions, they must transitively be traceable back to the source. Here's a valid model where all interactions in our model are on a path from the source stimulus. And an invalid model is one where you have an interaction, but the source is not actually on a path from the from the actual source of the pathway. So we'll be ruling out all models like the one on the right and be considering all models that satisfy this property. Coming to temporal constraints, we assert that our interaction paths should be consistent with temporal data. What does this mean? So we look for ways of annotating the nodes in our network, the proteins in our network, with timings of these activation or inhibition signals. So for A, B, C, D, we'll have to find some timing such that the data can support this chain of interactions. And in this example, we see that we can find evidence for A being significantly changing and being activated, and then as B has no data, we say that it can happen at any time, and we see that C can come later than A, and finally D can exhibit some inhibition activity that comes after C's activation. So this is a valid model that we would consider. In contrast, if our data look like this, there exists no way of assigning values for these timing annotations that would work with this data, because A, which is upstream of C, has to be activated after C. So this would be an invalid model. So now that we have these space of models, there is typically exponentially many of these sign-directed models that we get from our inputs. So for instance, here's a small example. As B is not observed, we assume that it can either be activated or inhibited by A. And our approach is to summarize the whole space of models. Instead of enumerating all of them, which is intractable because there are exponentially many in networks of hundreds or thousands of nodes, we summarize them with the property that if we see the same direction or sign in all models, we keep that in our summary. But if there is some ambiguity as to what an edge can be in different models, that becomes an ambiguous edge in our final network. So we applied our approach to some real data. So here's our case study. We stimulated EGFR cells with the EGF ligand and performed mass spectrometry analysis at 8 different time points. So it is here important that we have some early measurements that let us observe the early response due to the nature of the phosphorylation. And as a result, we observed around 200 significantly phosphorylated proteins. So our result was a network, a summary network that had around 400 edges, and we were able to assign a single direction to around half of these edges across all models that we considered with the constraints that we had. So if we had a direction, which means one of these 200 edges, it did not appear in the reverse direction in any of the models in the space. Similarly, we could assign a unique direction and sign to around 40 of these edges in the whole space of models. And our final summary network contains 83% of the phosphorylation activity that we have from our input data set. So compared to the 2% that the BioCarta pathway was getting, and we did some similar study of other manually created databases, and it was always 90% or more of the activity was missing from the databases. So let's look at, as an example, a subnetwork here. So the MAPK, in the MAPK subnetwork, to reiterate, the green and red edges are those that in all models have the same direction and sign, and the other black bold edges have a unique direction, but does not have a unique sign that we can assign. And we see that the diamond, actually this is not correct. The circle edges are those that are unknown to any of the EGFR pathway maps that we looked at. And we have the phosphorylation here given as the shade of the red. So here we can trace back to our constraints how they were used for inferring this data. The MAPK one was unobserved in the phosphorylation experiment, but the standard forest approach that we used recovered the node as being part of a high confidence interactions, even though it didn't exist in the data. And the activation of MKL1 was inferred by conjoining the temporal data that we had with the prior knowledge that we asserted as the kinase substrate directions. And this, these edges we were able to semi-automatically confirm with existing literature by using natural language processing tools, but I'm not going to go into the details of that because we are currently doing some more interesting analysis of actually experimentally validating some of these predictions that we have from the known parts of the pathway to the proteins that are not mentioned by any of the pathways. So here's our very preliminary work on trying to validate this interaction, ABL2 to CRK. Here we have the untreated case where the pathway is not stimulated. We have some normalized, some basal level normalized to 0. And then stimulating the pathway, we observe some activity around 4 minutes. We have a peak of CRK levels. And if we introduce an inhibitor of ABL2, we observe that the level of CBL is reduced, actually. So this is very preliminary, and we are working on trying to validate more of these. So in conclusion, we have an approach of declaratively stating constraints and getting the full set of models that agree with the actual dynamic signaling events that we extract from the temporal phosphorylation data. And we observe that the joint inference using multiple sources of data to which we could add more and add them as novel constraints to be considered within our system. And we also observed that the sum of these constraints together was more than the individual contribution. Asserting them together led to more predictions than, more unambiguous predictions than considering them alone. And we treat these ambiguity as a first-class citizen, and we detect only the non-ambiguous predictions across all valid models, and we are doing some experimental validation to support these. So I'd like to thank my collaborators, and we collaborated closely with Tony, who is here at the conference, and I would be happy to take questions.
The prediction problem looks like it closely resembles the network inference sub-challenge from last year's dream. Have you tried that on the open data set and scoring now? Would that have won last year's challenge? Or?
Yeah, that's a good question. We considered that, but our case, the case that we were focusing on was somewhat different from the setting at the Dream Challenge. So we were considering this sparse network, so we had to bring in this prior, the topology that might be linking the nodes by using unobserved data. So that seemed a little bit different than what the Dream Challenge was addressing, but they are similar, yeah.
The winner last year did use prior information, although it combined it late. It actually looks like your model might outperform that, so theoretically anyways.
So yeah, that would be something that we would
okay. Thank you.
Maybe testing, yeah.
All right, thanks, Ali.
Thank you.